Welcome everyone. This is Dayan. I'm an assistant professor from the Computer Science Department of the University of Alabama at Birmingham. Today, I will present this tutorial together with my PhD student, Guimu Guo. The topic of our tutorial is Systems and Algorithms for Massively Parallel Graph Mining. This tutorial will be split into two parts. Part 1 will be presented by me, where I will first motivate a categorization of graph mining problems from the perspective of algorithm time complexity, followed by an introduction of how to conduct graph mining using think-like-a-vertex framework. I will then indicate the weakness of such frameworks in addressing compute-intensive graph mining problems to motivate our task-based mining frameworks. Finally, I will walk through the design of Prefix FPM, a compute-intensive system for frequent pattern mining in general, including the problem of frequent subgraph pattern mining. Part 2 will be presented by my PhD student Guimu Guo, where he will walk through the design of our G-Sync system that follows a think-like-a-subgraph programming model, followed by an introduction on how to write parallel graph mining algorithms on top. Guimu will also be concluding this tutorial. Now, let's first look at how we can categorize graph mining problems. Since we are considering to parallelize graph mining in a parallel and even distributed environment, the target problem's time complexity actually plays a key role in deciding which parallel framework design is appropriate. So we will focus on a categorization driven by the problem time complexity. Relational database has been popular for many decades, thanks to the powerful set of relational operators, such as select and join, that can be assembled to answer all kinds of queries on tabular data. Unfortunately, the operations on graph data have been very heterogeneous, and the graph data management has not been fully unified, despite recent efforts by graph databases such as Neo4j and by graph query languages such as the new GQL standard. In the domain of parallel programming frameworks, there have also been attempts to unify many different graph algorithms under one framework. These frameworks often adopt a simple programming model that is more flexible and general, but the performance really hurts, since the problem-specific optimizations cannot be utilized. A researcher, Frank McSherry, has actually wrote a workshop paper in HotOS to criticize the performance suffering of existing graph parallel frameworks. To understand better why different graph algorithms need different parallelization frameworks, let us look at some popular graph problems from the perspective of time complexity. One problem is to find the k-call of a graph, which is the maximal subgraph where each vertex has a degree no smaller than k. In fact, we can go one step further to do k-call decomposition, which basically computes k-call for all k values. It is well known that k-call decomposition can be done in linear time using a peeling algorithm that iteratively removes vertices with the smallest vertex degree. So even if this particular algorithm also finds dense subgraphs, it nevertheless has a low time complexity. Another problem is random walk, as represented by algorithms such as PageRank. These algorithms also have a low time complexity since they are iterative, where in each iteration a message is passed along each edge, and the algorithms usually run for a small number of iterations. In contrast, some other graph mining algorithms are NP-hard. Examples include mining pseudo-clique structures such as quasi-cliques and k-plexes, and mining frequent subgraph patterns. We identify the following desirable design goals that a big data framework should possess, and this is actually what made the simple MapReduce model popular more than 1 decade ago. Firstly, A big data framework should be easy to program, even for those programmers who know nothing about parallel programming. Believe it or not, such programmers are actually the majority. And that's why, even though MPI has many similar functions for gathering and scattering data, as well as MPI reduce operations, MapReduce was so much more popular until Apache Spark beats it with more transformation functions that are easier to use. In the big data systems domain, the priority is never about technical sophistication, but user-friendliness. So API design is a key to the success of a framework. However, performance is equally important since that's the purpose of using a parallel framework to operate on big data. Another important aspect of big data frameworks is that the programming model should cover a reasonably large range of problems, so that it is worth users' time investment to learn a new API, and so that the execution engine can be reused for different problems. However, this does not mean that the big data framework you design should be able to do everything. Since the more general your computing model is, the less opportunities there are for problem domain-specific performance optimizations. In general, there is a trade-off between the three metrics shown on this slide. That is, how easy to program, how many problems are covered, and how efficient your computing model can run. A common mistake that researchers make is that they propose simple programming APIs that can apply to a lot of problems, so that a research paper can be written in an elegant way. But the performance is actually terrible and against the first two V's of big data, that is, volume and velocity. Of course, when everyone is doing this, you can always find a slower baseline to compare with in your paper. This is especially severe for problems where the time complexity is high. My group solves this performance problem by pinning the execution efficiency and the programmability to be high and adjust the problem coverage so that each of our systems can solve a reasonable range of problems but still being able to utilize domain-specific performance optimizations. One solution that we propose along this direction is to keep CPU cores busy for compute-heavy problems by utilizing divide and conquer, which we shall explain throughout this tutorial. Specifically, we divide the graph mining problems based on their algorithm time complexity. We then develop dedicated frameworks for each problem category. And as we emphasized earlier, we pin the two metrics to be high, that is, programmability and execution efficiency. Different frameworks can interoperate in the Hadoop ecosystem, so there's no need to make them unified under the same framework. The first category of graph mining problems that we define are iterative algorithms. These algorithms have a low time complexity, usually passing messages between vertices along edges, and running for a logarithmic number of iterations, giving a time complexity of about n polylog n. Here is a list of papers that advocate the design of iterative algorithms following this n polylog n complexity paradigm in order for these distributed algorithms to be scalable. Problems following this category include random walk algorithms such as PageRank, machine learning algorithms such as belief propagation, and alternating least squares, all of which follows an iterative algorithmic workflow. We can see that those problems have a linear-sized output, typically one score for each vertex or each edge. The second category of graph problems we identify is frequent subgraph pattern mining. Here, you want to find the subgraph patterns that frequently appear in a graph database. The graph database can contain many graphs, such as chemical compounds, or it can keep a big graph, like an online social network, or a knowledge graph. Besides the frequency criteria, we can also add other restrictions, such as pattern closeness and pattern maximality. However, it is well known that frequent pattern mining is NP-hard, meaning that the problem time complexity is very high, needing a lot of CPU time to compute, even though effective pruning rules can eliminate a lot of search space. The third category of graph problems we identify is structure-constrained subgraph mining from a big graph. Here, you want to find subgraph instances that satisfy some predefined criteria from a really big real graph, such as an online social network. Example applications include dense subgraph structure mining and subgraph matching. Although the latter is a query, not a mining task, so it's not our focus in this tutorial. It is well known that these problems are NP-hard, so they also need a lot of CPU time to compute. Unlike iterative algorithms in category 1, where the output size is linear to the size of the input graph, the last two categories of problems output subgraphs that may overlap, and the output size can be exponential. Next, I will introduce the first category of graph mining problems that are solved by iterative algorithms. I will focus on the think like a vertex programming model that is used to parallelize such algorithms. In the think like a vertex programming model, or TLAV in short, information on vertex states are passed as messages along edges, and the vertices update their states based on the received messages until all vertex states converge. The output of a TLAV algorithm is usually one value for each vertex. In a TLAV programming model, users specify a user-defined compute function as shown on the right to indicate how a vertex processes its received messages to update its state and to generate outgoing messages in an iteration. In this example, we are looking at PageRank computation, where a vertex adds up the received messages and assigns the summation as its new PageRank value, and in the meanwhile, evenly distribute the summed value among its outgoing neighbors. We can see that if we distribute vertices on different machines and pass messages through the computer network, the CPU cost of summing messages is not a bottleneck compared with the communication cost to receive and send messages. Here is a list of research papers studying how to develop TLAV algorithms. And notice that TLAV is for general graph problems with a low time complexity, not just for graph mining problems. In the last paper by Shui Liu and Robert Tajin, they showed that for computing the connected components of a big graph in parallel using the TLAV paradigm, we need an algorithm with a time complexity of n polylog n. We know that a serial algorithm to compute connected components by depth-first search takes only linear time, so the total workload may increase when we move from a single-threaded algorithm to a parallel one. We also remark that even this n polylog n time complexity is not easy to achieve as a parallel algorithm, and a technique called point jumping is necessary to allow the number of iterations to be logarithmic. A natural question to ask is, why we care about parallel computing if a serial algorithm has a linear cost? The main motivation is that our input graph can be huge, so you want the graph to be loaded from many disks in parallel to benefit from the total disk bandwidth, which can be achieved if your data is kept on Hadoop distributed file system. Also, your job may just be one operation in a long data flow on top of the Hadoop ecosystem, so you want to use a Hadoop-compatible framework. More importantly, your laptop may not have enough memory space or even disk space to keep such a big graph. Last but not least, you only need to define a compute function for a vertex in the TLAV API, which is much faster to implement. There have been a lot of papers developing systems where users can program graph algorithms using the TLAV API. However, we would like to remark that a lot of them only focus on applications where a vertex can aggregate the messages received along its incoming edges into one value to be used in the compute function, such as the messages summation in PageRank. but this is a narrower subset of what a general TLAV API can solve. For example, they cannot support point jumping algorithms. However, since those systems focus on a narrow set of algorithms, they can utilize more optimization opportunities. GraphLab is such a system, while others like Pregel and Giraffe are more general. In fact, Google's Pregel is the first TLAV system, and so all these systems are often called Pregel-like systems. We will mainly discuss Pregel in this tutorial. Before introducing Pregel, I would like to point out that GraphLab follows a quite different design. Specifically, it uses a so-called vertex cut partitioning method, where edges are distributed to different machines rather than vertices. Since different edges of a vertex can be in different machines, the state of this vertex needs to be mirrored to all those machines. GraphLab's vertex program is also a bit different. Following a gather, apply, and scatter programming model, here each vertex can directly access data from its adjacent vertices and edges, since they have been mirrored in the current machine. But data synchronization is needed for data consistency. Pregel's model is cleaner, without mirroring vertex and edge data. As we have indicated, Pregel is a pioneer of the TLAV model. Unlike GraphLab, where you directly take data from adjacent vertices and edges, a vertex passes messages to other vertices to propagate information updates. The computation is also iterative, where in each iteration, vertices pass messages to other vertices, and these messages will be received in the next iteration. I have not heard how much impact Pregel has inside Google, but it definitely has inspired many research on TLAV models in academia. The Pregel paper actually won the Test of Time Award in Sigma 2020. Given a big graph, Pregel partitions vertices into different machines by ID hashing, where each vertex is accompanied with a list of its neighbors that it can send messages to. Each vertex U is associated with a user-defined function, where the input argument is a set of messages received by U from the previous iteration. Inside the compute function, a vertex can send messages to other vertices, get the current iteration number to determine what action should be taken, and deactivate itself by voting to hot. Note that so far we have not explained how a Pregel job terminates. This is actually achieved by setting the active status of vertices. Specifically, each vertex has a status flag indicating whether it is active, and an inactive vertex can also be reactivated if it receives a message in the current iteration. A Pregel job terminates if, after an iteration, all vertices are inactive, and meanwhile no messages have been sent in this iteration, since otherwise some vertex will be reactivated in the next iteration. In the next few slides, we will go through some graph mining problems that can be addressed in the TLAV paradigm of Pregel. One example is to compute connected components, where in the compute function, a vertex receives messages on the smallest vertex IDs that its neighbors have seen. Find the smallest received ID among those messages. And if the value is smaller than the smallest ID that the current vertex has seen before, we will update the smallest ID seen by the current vertex, and broadcast this ID to all its neighbors. A vertex always votes to hot at the end of an iteration. We illustrate this process using a graph with two connected components. Initially, every vertex only sees its own ID, and will broadcast this ID to its neighbors. In the second iteration, for example, 0 will be passed to vertex 5, and since a smaller ID is received, vertex 5 will update the smallest ID it sees as 0 and send 0 to its neighbor 0 and 7. In iteration 3, vertex 7 will receive message 0 from 5, so it will update its smallest ID seen as 0 and broadcast 0 to its neighbors. We can see that no vertex can receive a smaller ID in the next iteration. So in iteration 4, no vertex will send messages and all vertices will vote to hot. Therefore, the job ends in 4 iterations, and the value at each vertex is the smallest vertex ID in its connected component. We can get the connected components by grouping vertices using that ID value that is achieved finally. Next, let's consider how to compute the k-call of a graph. We will illustrate the algorithm assuming that k equals 3. That is, we want to find the maximal subgraph where each vertex has degree at least 3. In the compute function, if the current vertex finds that its degree is less than k, it deletes itself and in the meanwhile sends messages to its neighbors to notify them to remove the current vertex from their neighbor list. A vertex always votes to hot at the end of an iteration. And we have indicated earlier, the vertex will remove those vertex IDs that it receives from its neighbor list. Here in iteration 1, the green vertices will find their degrees to be less than 3, and thus they will remove themselves from the graph. In iteration 2, the yellow vertices find their degrees to be less than 3, and thus they will remove themselves. In iteration 3, all vertices find their degrees to be at least 3, so there's no more messages passed, and all vertices vote to hot at the end, which terminates the entire Pregel job. The remaining graph shown here is the 3-call of the input graph. Next, let's go one step further and consider the problem of k-call decomposition, which for each vertex computes the largest k that this vertex is in a k-call, which is called the vertex call index. We have shown the call index of every vertex on this slide. Next, we explain how the compute function looks like. In the first iteration, every vertex initializes their value as their vertex degree. Then, in each iteration, a vertex computes an edge index operator, which we explain next. Consider this vertex. We will get all its neighbors' values into a list and sort them in non-decreasing order. These values can be broadcasted by its neighbors in a previous iteration. Here, the third value is the current call value from a neighbor, and it equals 3. The edge index operator scans from the first number until we reach a call value that equals the number of values scanned in the list, for which we call the support. Here, after scanning 3 values, the third value equals 3, so the edge index operator returns 3. Note that in the local neighborhood of the current vertex together with the first 3 neighbor vertices, every vertex has a degree at least 3. So, the call value of the current vertex is reduced from 6 to 3. The TLAV algorithm for call decomposition basically lets every vertex repeat this edge index operation to reduce its call number iteration by iteration until the call values of all vertices no longer change. We can prove that the final values are the call indices of the vertices. There is another work that I think is worth mentioning, which is a meter system that advocates a model called Data-Based Accumulative Iterative Computation, or DIAC in short. This is an asynchronous model which allows different vertices to run different number of iterations, so that those vertices that converge slowly can do more computations. GraphLab also allows asynchronous computation, but the method is a bit cheating. It basically does not propagate value changes less than a small threshold epsilon, so that some almost convergent vertices will not participate in computation. But such small changes are lost, and the method is approximate. Meter, on the other hand, directly computes on the value changes rather than vertex values themselves, and is an exact method. Value changes to a vertex are never lost, but accumulated until being large enough so that the vertex is scheduled for computation. Meter is applicable to a lot of problems, where the message values can be aggregated into one value. So its problem scope is the same as the gather, apply, and scatter model of GraphLab. Meter also does not need to mirror vertex and edge values. Surprisingly, although Meter seems to be superior to GraphLab in almost all aspects, it does not receive as many attention as GraphLab, even though both systems support asynchronous computation. Here's a research timeline for big data systems. Since the proposal of MapReduce by Google in 2004 and the advent of Hadoop MapReduce, we saw an explosion of MapReduce-related research papers in the database community since 2009. Then, in 2010, Pregel is proposed by Google researchers to replace MapReduce for graph processing, to avoid unnecessary data dumping and loading through HDFS between iterations. Since Pregel was not open sourced, it took 2 years for the next Pregel-related research to appear. In OSDI 2012, 2 related systems were published, GraphLab and GraphQi. Since OSDI is a high-impact venue, I believe this line of research was gaining a lot of attention at that time. Meanwhile, in NSDI 2012, the Spark paper was published as a replacement technology for MapReduce. The key idea is to hold intermediate data in distributed memory rather than on HDFS, and add more transformation functions that can be accomplished, say, as map-only jobs. The next year, in 2013, Giraffe was born, which is considered the open-source replication of Pregel, though Giraffe is in Java. So where was I at that time? I was doing my PhD study on algorithms research in Hong Kong. And at my final year, from 2013 to 2014, I started to pay attention to graph parallel systems, thanks to the access to a Hadoop cluster invested by my postdoc advisor that I started to collaborate with. I then moved to the Chinese University of Hong Kong to continue Pregel-related research for 2 years, until I became an assistant professor in the US in 2016. We did pretty well in Pregel-related research, and I won the Hong Kong Young Scientist Award in Physical and Mathematical Science for the year 2015. In retrospect, I think the key reason we were successful at that time is that Pregel research was just started in 2013 with a lot of research topics and opportunities that can be explored to do foundational works. And the competition at that time is not high. Overall, I think finding a research direction is essentially balancing the 3 aspects: difficulty, productivity, and competition. I was fortunate that the productivity dimension for Pregel research was promising in 2013, and the competition was not high. Now this direction is a bit crowded, and a lot of good ideas have been explored. As a comparison, just for fun, deep learning has become a hype in recent years, and if you get the basic concepts and learn a bit Keras or PyTorch via YouTube videos, you can easily program awesome models yourself, and the math is hidden by Keras or PyTorch functions totally. As you can imagine, while the difficulty is not very high, and the productivity can be quite high. There are a lot of competitions in this direction. One researcher that I admire a lot is Kai-Ming He, who is the inventor of a lot of important things like ResNet, fast RCN, and He initialization. As you can see, his citation is crazy, which reflects how crowded the AI area has become. It is also contagious, and in the database community, we see a lot of deep learning methods used these days. I'm quite surprised to learn that there is a work even trying to replace the efficient B+tree index with a deep learning model. Now, let me briefly introduce the graph parallel frameworks we developed that improved Pregel's design from various aspects. All the frameworks shown here are in the form of C++ libraries, which can be used to implement iterative graph parallel algorithms. Pregel Plus improves over Pregel by proposing techniques to reduce the number of messages transmitted. Block-O groups vertices into blocks to eliminate communication within each block, and it proposes a corresponding think-like-a-block programming model. Pregel adapts the TLAV API for interactive online graph query. GraphD scales Pregel further by supporting distributed out-of-core execution. LWFT proposes a faster method for fault tolerance and recovery than Pregel's original checkpointing method. Here's the graph parallel ecosystem that we developed, called BigGraph at CUHK, and can be accessed using the URL below. You can also directly Google BigGraph at CUHK to find the system websites. Notably, all our frameworks load graph from HDFS and can write results to HDFS, so they can interoperate with other frameworks in the Hadoop ecosystem. You can see that the previously mentioned works are well cited. We also have 2 books on this topic, with comprehensive review of not only our own frameworks, but also other important state-of-the-arts in the field. In this PVLDB 2014 paper, we proposed the concept of PPA, which is a class of scalable Pregel algorithms that runs for a logarithm number of iterations, and each iteration has a linear cost. We designed PPA for a series of fundamental graph problems, such as list ranking and connect components. And these PPAs can be used as building blocks to implement PPAs for other more advanced graph problems. This work was highly commented by peer researchers, such as this slide from a tutorial in VLDB 2014. The list ranking and the connected component PPAs have been applied for genome assembly in our ICD 2018 short paper. An extension of this work has also been accepted by TCBB. In another PVLDB 2014 paper, we proposed a novel system called Block-O, which groups nearby vertices into subgraph units called blocks, so that message passing only happens among blocks. Within each block, a serial algorithm can be run to propagate vertex states without any network communication. Based on this design, we also propose a new programming model called Think Like a Block for users to write their distributed graph algorithms in Block-O. The performance improvement is significant. For example, a Pregel job that runs for 1 hour can now finish in 10 seconds in Block-O. To efficiently create blocks, Block-O supports an automatic graph partitioner based on the idea of graph Rhodolic diagram, which is highly efficient to execute. Block-O has also been highly commented by peer researchers. For example, in this PVLDB 2018 paper, the authors compared many graph parallel systems and found Block-O to be the overall winner. In this W 2015 paper, we propose two message reduction techniques to reduce the number of messages transmitted through the network in Pregel, without the need of making any changes to the original TLAV API. Since the second technique is for point-jumping algorithms, which take time to present, here we just briefly explain the first technique, vertex mirroring. As this diagram shows, if many vertices on a machine need to send messages to the same vertex in another machine, then messages can be combined into one message for certain applications. An example is our PageRank application, where we can simply sum the message values and then just send the summation over the network. Pregel has a mechanism called message combiner to implement this idea. In contrast, we found that if a high-degree vertex needs to broadcast its value to the neighbors, it needs to send the same value many times to each machine, such as vertex U4 here. A solution would be to send the vertex value to its mirror in another machine, and let the mirror forward the message value to each local neighbor, without communication. We found that message combining and vertex mirroring are mutually exclusive. For example, the message from U4 to V2 cannot be combined with those from U1, U2, and U3 in this diagram. We should only mirror high-degree vertices to allow messages of low-degree vertices to be combined, and our paper derives an optimal degree threshold for vertex mirroring. In this PVLDB 2016 paper, we proposed to redesign Pregel that was originally designed for offline graph processing towards online graph query answering. The motivation is that the TLAV API is very user-friendly to write algorithms to answer graph queries, such as shortest path queries and reachability queries. But those algorithms are lightweight and visit only a small portion of the whole graph. They also often rely on an index to speed up query. Our Pregel framework achieves those goals, where graph indexing is supported and each online query only visits a small number of vertices, while the query answering algorithms are still written in the TLAV paradigm. Compared with Giraffe, where a shortest path query on a Twitter graph takes 100 seconds to finish, Pregel can answer 3 such queries in just 1 second. The systems we see so far are all in-memory systems, where the adjacency lists and messages are kept in main memory. This is actually not necessary in Pregel, since message passing is the bottleneck in a typical Ethernet environment. And if we keep the adjacency list and messages on local disks for streaming, and overlap the disk I/O operations with the network I/O operations, the running time will not increase. In this TPDS 2018 paper, we propose a GraphD system that keeps adjacency lists and messages on local disks for streaming during the execution, so that the memory cost is negligible. As a result, GraphD can scale to very big graphs. We observe GraphD has the same performance as our in-memory Pregel Plus system, meaning that the significantly reduced memory consumption is a free lunch. Regarding fault tolerance, existing Pregel-like systems rely on checkpointing. For example, in PageRank computation, we can write the current status of computation to HDFS every 10 iterations, so that, for example, if a job fails in iteration 98, it can load the checkpoint saved at iteration 90 and rerun from there, rather than rerun from the first iteration. Pregel needs to save everything into a checkpoint, including messages and adjacency lists. This is because some vertices may become inactive and do not send messages, and some edges may be deleted during the computation, such as in our Pregel algorithm for K-call presented earlier. In this ICPP 2019 paper, we propose to only save vertex states to a checkpoint, and regenerate messages from them during recovery. For edges, we propose incremental checkpointing that only logs the edge updates for replay during recovery. We also propose to let machine log messages locally, so that during recovery, only those messages from failed machines need to be transmitted. These techniques improve the performance of checkpointing and fault recovery by over one order of magnitude. So far, we have been looking at Pregel-like frameworks that adopt the TLAV, or Think Like a Vertex, programming paradigm. TLAV looks great so far for iterative graph algorithms that belong to category 1 in our categorization of graph mining problems. So, people naturally will extend it to solve other graph mining problems, including those NP-hard ones that we introduced earlier in categories 2 and 3. As expected, the performance reported is often terrible. But at that time, there were no other parallel framework choices. Our tutorial from now on will explain how we fill this gap. Firstly, let's understand why TLAV systems are inefficient when it comes to compute-intensive graph mining problems. As we have seen, not all graph mining problems exhibit the same characteristics, with some being I/O-intensive, such as those we just presented, and others being compute-intensive, where the bottleneck comes from the enormous CPU time needed, not the data volume. Such problems include mining dense subgraphs from a big graph, as in our category 3, and mining frequent subgraph patterns from a graph database, as in our category 2. As a breakthrough in this area, we have developed a distributed framework called gsyncer for mining dense subgraphs, which will be presented by my student Guimu Guo. We have also developed a parallel framework called the Prefix FPM for mining frequent patterns in general, which I will introduce next after motivating why TLAV systems are inefficient when going beyond iterative data-intensive graph analytics. It is worth noting that the current excitement of big data systems are nothing more than building data-intensive frameworks, where different data partitions can be streamed in parallel, and messages can be exchanged in parallel. They are good for I/O-heavy operations, but the aggregate I/O bandwidth utilized is often comparable or even less than the throughput of a single CPU core, as indicated in this post by Frank McSherry. Frank McSherry thinks that people are overexcited about big data systems, and people are developing systems with poor performance. In fact, data-intensive frameworks have communication as a bottleneck, and CPU cores are often underutilized. For example, if each data block generates an amount C of communication, and your network bandwidth is only 2C, then even if you have many CPU cores, you can at most fully utilize 2 CPU cores, which is a waste of resources for compute-intensive problems. A lot of problems are actually compute-intensive, where the workloads come from the exponentially large search space rather than the large data volume. If we address them using a data-intensive framework, we achieve a throughput that is similar to a couple of CPU cores on a single machine at best. In fact, things can get even worse given that the network throughput can be much lower than that of a CPU core, and the I/O bound execution slows down the entire process. For example, in this TKDD paper, the authors find that for triangle counting, the single-threaded algorithm is 10 times faster than the state-of-the-art MapReduce solution, running with over 1,600 machines. Despite these criticisms, no solution was proposed. The solution is to make the execution engine of a framework compute-intensive by itself. We have proposed a new paradigm called T-Syncer or Task Syncer. which utilizes divide and conquer to achieve compute-intensive execution. The key insight is that a lot of problems can be represented as tasks, while a big task of a big dataset can be decomposed into independent tasks over smaller data subsets for parallel execution. So, if the data needed by a task is large enough, the linear cost of fetching data into a local machine is well offset by the subsequent compute-intensive mining of the fetched data. And the concurrent execution of multiple tasks can hide the communication latency. In this tutorial, we are advocating the development of big data programming frameworks following the T-thinker paradigm. This is a new area like Pregel research a decade ago, with many research topics to explore and a low degree of competition. We have already obtained a number of successes, and we are also working on a number of works along this line that can be fundamental. It's time to make impacts, and if you start investing in this research direction, you could be another Coming He 5 years from now. Of course, task-based execution has been there in the HPC community for a while, so the contribution of a task-based big data framework should be that the programming model is easy for the targeted category of problems. However, existing pioneering frameworks in graph mining simply materializes and grows all potential subgraphs in the search space, the cost of which is prohibitive. Examples include the embedding-centric API of Arabisk that attempts to handle both dense subgraph mining that allows backtracking without subgraph materialization and frequent subgraph pattern mining that needs pattern deduplication by subgraph isomorphism check. Since the problems are quite different in nature, a unified design actually leads to the worst of both worlds. Note that dense subgraph mining is a pattern-to-instance process, where you have a pattern in mind and find subgraph instances in a big graph that satisfy that pattern. In contrast, frequent subgraph pattern mining is a reverse process that discovers new subgraph patterns. You do not have any patterns in mind initially, but you examine the subgraph instances to evaluate whether a subgraph pattern is frequent or not. We will explain this in more detail later in this tutorial. Our G-thinker system addresses the dense subgraph mining problem by spawning tasks from individual vertices to grow candidate subgraphs for mining. And the big tasks can be decomposed into smaller tasks to divide the workload by multiple CPU cores. G-thinker will be presented in detail by Guimu. In the last part of my talk, I will introduce how we design Prefix FPM, our compute-intensive framework for frequent pattern mining, which can be used to mine frequent subgraph patterns from a database of graph transactions. The graph mining problem we consider here is frequent subgraph pattern mining. This problem is illustrated by this slide. Here, we have a graph database of 4 chemical compounds, and pattern OH appears in 3 of them. So if we require a pattern to appear in at least 3/4 of the graph transactions, OH will be considered as a frequent subgraph pattern. Let us first illustrate the concepts in frequent pattern mining using item sets as patterns. In this slide, we have a database of 6 transactions, indicating the items that people bought from a supermarket. From this database, we would like to mine patterns in the form of item sets, where an item set with 3 items is shown at the bottom here. For a pattern, we have the concept of pattern length. In our item set pattern, the size is 3, since we have 3 items in the set. If we check the item set against the database, we can see that transactions 4 and 6 cover our item set. and therefore we say that the support count of our pattern is 2. We can also define support as a fraction of transactions in the database that cover our pattern, which is 1/3 in our case. We remark that the pattern type is not limited to item set. Depending on the database type, a pattern can also be a subsequence, a subgraph, or even a subtree. Besides the chemical compound database we saw earlier, another example is to mine subtree patterns from XML files, such as those from DBLP, to capture patterns like frequent co-authorships in a particular conference. It is also common to add constraints to the desired patterns, such as the requirement that 2 elements in a sequential pattern cannot be more than 3 elements away in a sequence transaction. In this slide, we show a tree-structured transaction, and we consider embedded patterns which only require the preservation of ancestor-descendant relationships between nodes. Then the pattern BBD is covered, even though it is not an induced subgraph of this tree transaction. In fact, frequent pattern mining is NP-hard, and it is important to utilize all the CPU cores in a multi-core machine for effective pattern mining. Therefore, we aim to design a parallel framework that is able to keep all CPU cores busy in mining frequent patterns. Another important goal is to make our framework's programming interface general enough for mining all kinds of patterns. We remarked that the pattern of item set is special because there's no order over the items in a set. So we can use algorithms that define its own order for effective mining, such as the FP growth algorithm. However, we do not target this problem, as it has been well solved by Google's parallel FP growth algorithm, which is shown at the top. We consider those patterns where it matters how the elements are ordered or connected. Our framework is designed based on the idea of prefix projection, the idea of which will be reviewed shortly. Our framework is called Prefix FPM, as we use prefix projection and tackles general frequent pattern mining, or FPM in short. An important feature of prefix FPM is that we consider algorithms that check patterns in the depth-first order of pattern growth. Let us now illustrate the idea of prefix projection by considering the problem of mining frequent subsequence patterns from a sequence database. Here, we can see that database D has 4 sequences. If we consider pattern A, then S4 is filtered as it has no A. And the underscored positions are those that match A. We call such a database as a projected database, projected by pattern A. Now, if we grow pattern A with one more element B, we only need to continue matching from the projected database of A. We will continue to match B starting from the underscored positions. This will give us the projected database of AB. We can further grow the pattern by C and check against the projected database of AB to find those sequence transactions that contain pattern ABC. Prefix span actually checks the patterns in depth-first pattern growing order. Let us consider a sequence database where there are only 3 element types, A, B, and C. We will first grow an initial empty pattern by A to obtain A's projected database. If it contains sufficient transactions, we will consider A as frequent and output. We can then grow pattern A into AA, create its projected database from that of A. Assume that the project database does not have sufficient transactions, so AA is infrequent. then AA is pruned and we do not need to grow AA further. After backtracking to pattern A, we will consider the next child pattern AB and assume that it is frequent. Then we will continue to check its child pattern ABA, ABB, and ABC. We will continue to check all the patterns in depth first order of the pattern growth tree until all frequent patterns are found. This algorithm has several desirable features. Firstly, we only check a child pattern of its parent pattern's projected database, which gets smaller as the parent pattern grows in size. Secondly, we can prune the whole subtree in our pattern search space once a pattern is found to be infrequent. Thirdly, we will remember how a parent pattern is matched to each transaction, so that a child pattern can continue its matching rather than starting from scratch. Finally, all child subtrees can be checked independently, and therefore are amenable to parallel computing. We remark that this prefix projection idea is not limited to mining sequential patterns. For example, we can find subgraph patterns from a graph database in a similar manner. For this purpose, we need to encode each graph pattern into a sequence representation. This allows us to run a prefix span style algorithm on the encoded sequence pattern space. This will, however, give rise to duplicate patterns, since different sequences can correspond to the same subgraph. Taking tree patterns as an example, where we do not differentiate the order of child nodes. Here, we can simply encode a tree pattern using depth-first node traversal, except that we need to add a $sign each time we backtrack. For example, for the first tree, we have B, A, B, $, D, $, B, $, C, $. We can see that the other two trees are the same pattern, but with different children order. But their encodings are different. Therefore, a canonical encoding is uniquely defined for each pattern as the smallest sequence encoding among that pattern's all possible encodings. During the actual mining, we only consider and grow a pattern if its encoding is canonical. As the pattern search tree shows, G0's encoding is canonical, but G1's is not. G1 and G0 are actually the same subgraph pattern, and therefore we prune G1 to avoid duplicated pattern checking. Pattern growth is usually by an additional element each time, and the subgraph patterns also do not need to consider all growing possibilities. For example, we do not need to consider growing from node 2 in this slide, since X is not on the rightmost path. This is because our encoding is in depth first order, and an earlier encoding in the DFS order should have considered that branch. Now, let's briefly overview the related work. There are a lot of earlier works that adapt the a priori algorithm on MapReduce to grow patterns in a breadth first order, where patterns of size I is checked only if all smaller patterns have been checked. For example, size 1 patterns will first be mined. These patterns are then saved to HDFS. The next MapReduce job will then load them back, mine size 2 patterns grown from them, and save to HDFS. They are then loaded back to mine patterns of size 3. A problem with such a MapReduce solution is that transactions and patterns are repeatedly saved to HDFS and then loaded back, which incurs a lot of I/O overhead. Secondly, the patterns need to be checked against the entire transaction database rather than a smaller projected database. A satisfactory solution that uses the depth-first FP growth algorithm is proposed by Google researchers, which make the FP growth algorithm run in parallel with a MapReduce job. The previous works are on item set patterns. Regarding subgraph patterns, a depth-first solution was proposed in ICD 2014, using 2 rounds of MapReduce. In the first job, transactions are partitioned among machines, and each machine only mines its local frequent patterns in depth-first order. These patterns are then unioned and given to the second job for refinement. This is correct because if a pattern is not frequent on any local transaction database, then it cannot be globally frequent. The work actually also incorporates some local patterns that are just below the support threshold to further improve the refinement performance. More recently, Arabisk proposes a very user-friendly programming interface for graph mining called embedding-centric. Here, an embedding is a materialized subgraph, and these subgraphs are still grown in a breadth-first manner for checking. Arabisk is a distributed system, and the subgraph materialization makes it I/O-bound. A follow-up work called RStream is a single machine out-of-core system that follows Arabisk's API, but is found to be more efficient. However, RStream is disk I/O-bound. We remark that Arabisk tries to combine frequent subgraph pattern mining with problems like click mining, but they are different problems. For example, clicks are predefined patterns, and the problem finds matched instances in a data graph. But our problem does not predefine subgraph patterns, but checks instances in our database to find these frequent patterns. In fact, Arabisk's API forces dense subgraph mining problems to conduct unnecessary subgraph isomorphism check, as well as subgraph materialization, which can be otherwise handled by simple node backtracking. Our G-Sync system satisfactorily addresses these weaknesses, and please check out Guimu's presentation on G-Sync. We adopt a task-centric computation model, where each pattern is associated with a task. The task will check if that pattern is frequent, and if so, it will grow the pattern by one more element to generate child patterns for further checking. If the projected database is big, child patterns are wrapped into independent tasks, which are then added to a task queue to be fetched by other threads for mining. Otherwise, the task is efficient to process by the current thread itself, so the thread will directly process it in depth-first pattern growth order. This slide shows how a thread processes a task, while line 2 first checks if we need to skip the current pattern. For example, its encoding may not be canonical. Then line 4 will generate child patterns and their projected databases. Each child pattern is then processed in the while loop, while line 7 checks if we should wrap child patterns into tasks for concurrent processing. Otherwise, the current thread will call the same function in line 13 on the child pattern to check and grow it recursively. We make the task queue a stack so that tasks are fetched in depth-first priority. This strategy prioritizes old tasks to minimize memory footprint occupied by the projected databases that are being mined upon. Our programming interface is shown here, where we have covered those user-defined functions of the task base class in our previous slide. There is also a worker class, which creates the initial size-1 pattern tasks and puts them into the task queue for concurrent processing, which is by the setRoot function, which is also user-defined. Here, we illustrate how our parallel framework divides the pattern search space. For example, thread 1 could be processing pattern AB. The next pattern in depth first order, which is AC, is fetched and processed by thread 2. Then, thread 3 and thread 4 will process the next two patterns in depth first order. Note that these tasks may add more child patterns into the current task queue so that idle threads can then fetch them for processing. We also allow a pattern to be checked against a big projected database in parallel, which is helpful initially when there are not many tasks to keep all the mining threads busy. Here is a speed-up result for our parallel GSPAN algorithm for frequent subgraph pattern mining implemented on top of Prefix FPM, where 3 graph datasets have been tested. And we can see that the performance scales well with the number of CPU cores used. We have open sourced our code on GitHub with detailed documentation, and there's also a video demo for you to check out. We implemented 3 algorithms on top of our framework, which are parallel versions of prefix span for sequence patterns, GSPAN for subgraph patterns, and sleuth for embedded tree patterns. Our experiments show ideal speedup with the number of CPU cores in our server, which contains 32 CPU cores. We have recently added more applications on top of our Prefix FPM framework, including algorithms to find closed patterns. You can get the code for those applications from this URL. We also added a timeout mechanism to avoid the mining of a very big pattern subtree. For example, in case those patterns in the subtree are all frequent in the transaction database, which keeps the subtree growing bigger. Here, before entering each pattern, we will check if the task times out. If so, instead of continuing mining, the remaining nodes in this recursion level are wrapped as new tasks and added to the system to be scheduled. And backtracking happens to create tasks for upper-level tree nodes. For example, assume that we are mining this subtree in depth first order, and before mining pattern ABC, timeout happens. Then ABC will become a new task, and we backtrack to the parent level where AC also times out and becomes a new task, followed by B and C. We can see that we do not over-partition a task in this method. For example, the subtree of node C becomes a new task, not any subtree and node C. Without any further delay, let's welcome Guimu to give the second part of this talk.